In this video, we are starting section 5.2 on strong induction. So our goals are to construct proofs using strong induction and to recognize when to use strong induction rather than our earlier induction, which is sometimes called weak induction. So what is strong induction? Suppose I'm trying to show some statement P of n is true for all integers n that are greater than or equal to some positive integer. So for example, maybe P of n is the statement show n can be written as a product of prime numbers. Okay, so I first want to talk about a shortcoming of weak induction when it relates to trying to show something like this. So the inductive step of weak induction involves assuming that P of k is true and showing that this implies that P of k plus 1 is true. That it's going to be true for the next integer up, k plus 1. In other words, we need to make a one-step jump from k to k plus 1. But sometimes the structure of a problem requires us to either make a bigger jump or multiple jumps. So why is this the case with this example? If I'm trying to show something like 120 is a product of primes, one of the things I might notice is 120 is 10 times 12. And if I already knew that 10 and 12 could be written as products of primes because, 10 is 2 times 5, and those are both prime. And 12 is 2 times 2 times 3, and those are now all primes. Well, I could just multiply these two equations together, and then I'd get 120 equals these primes times these primes. So that would show 120 is a product of primes. So, to be able to get to that, I'm using the fact that, I can do it for 10 and 12, and I'm trying to use both of those to jump up to making a statement to 120. So I need to make more than just a one-step jump, because I'm trying to get from 10 to 20, and then to 120, and then 12 to 120. So in other words, we need a stronger assumption now, rather than just a one-step jump. So let's make this a bit more formal. Let's first talk about this visually. So the idea of strong induction is I'm going to represent P of 1, P of 2, P of 3, and so on using dominoes. So let's suppose we know the following. Let's suppose I know that the first domino falls, and here's where it's going to be different from just our regular weak induction. Now, instead of just assuming that domino k falls and showing that that means the next one falls, I'm going to assume that dominoes 1, 2, 3, all up until k, that if they all fall, so if the first k all fall, then the next one falls. Okay, so if the first k fall, then domino k plus 1 will also fall. So I'm going to assume that that is true for any arbitrary positive integer k. So if I put these two things together, the first part says the first domino falls. Well, that is enough to guarantee the second one falls by this second part. And now I know the first two dominoes fall. And if the first two dominoes fall, well, that means the next one falls after that, the third one. So now I know the first three fall. And the second part then tells me, well, that is enough to then say the fourth one falls. And we'd keep going like this. So altogether, this will now show that all the dominoes will fall. I still arrive at that same conclusion. I just have a stronger assumption I'm getting to work with. I'm assuming now not just that domino k falls, but that all the dominoes up until domino k will fall. Okay, so let's formalize this a bit. So strong mathematical induction says that to prove a statement Pn is true for all integers n that are greater than or equal to 1, there are two steps. There's the base step, in which we show P of 1 is true. Sometimes this value might be different from 1. It just depends on what our set is. Like if I'm trying to show it's true for all integers n greater than or equal to 3, then it started off with P of 3. And we'll see an example of that and it being different from 1 in this video. In a later video, we'll even see an example of a situation where there's more than one base step. Okay, and then we have the inductive step. Now in the inductive step, I'm going to assume that not just P of k is true, but that everything up until then is true, that P of 1, P of 2, P of 3, all of those up until and including P of k are all true. So I'm assuming they're all true for an arbitrary positive integer k, and then I'm going to show that that implies p of k plus 1 is true. So writing this as an implication, I am assuming that if p of 1 and p of 2 and up until and p of k, if they're all true, then p of k plus 1 is true. All right. So let's take a look at an example. Let us prove this thing about these products of primes. So first, let's kind of more formally state what a prime is, but likely you've seen these kind of going back to, I don't know, maybe middle school, or would be the first time you would have seen primes, or maybe high school. So I'm going to let n be a positive integer. We say that n is prime if there are exactly two positive integers that divide it, 1 and n itself. So there's got to be exactly two positive integers that divide it. One of the things that means is that rules out 1. N cannot be equal to 1 because the only positive integer that divides it is 1. But there's got to be two distinct positive integers that divide it. So a number is not prime in two possible ways. Either if that integer is 1, or if there's another positive integer that divides n. In other words, if there exists some positive integer a that divides n. And when that happens, that a will be between 1 and n. Okay, that's something that we could show, but I'm just going to accept that as a given here, that if there is this third integer that divides n, it'll be between 1 and n. Okay, so before I get to my statement that I'm trying to show, this is actually, there's a more specific version of this that has a famous name. The fundamental theorem of arithmetic says that if n is a positive integer that's greater than or equal to 2, it has a unique prime factorization. So for example, 18 is 2 times 3 squared, and that's the only possible prime factorization of 18. So the word unique here means that there's only one. Okay, so we are going to prove a slightly weaker version of this, which is the problem that we saw at the beginning, that if n is an integer greater than or equal to 2, I'm going to show that it can be written as a product of primes. Okay, so I'm not going to worry about this unique part. I'm just going to show that it can be written as a product of primes. So first, I'm going to get a feel for this by playing around with a few values of n. So if n was 4, I notice that 4 is 2 times 2. So here I have two primes multiplied together. So this is a product of two primes, this prime and that prime, multiplied together. Something like the number just straight up 2, well, that's already prime. I don't have to write it as, a bunch of these things multiplied together. I could just write 2. So I say that that is a product of one prime. Similarly, 3 is prime already. I don't have to multiply it by any other primes. That is also just a product of one prime. It's just 3. Let's do a bigger one. If I look at 60, 60 is 2 times 30, and I can factor a 2 out of 30, and then it's 2 times 15, and 15 is 3 times 5. So that's how I can write 60 as a product of primes. So this is a product of 4 primes. And if I were to keep trying other values of n like this, we'd always be able to express them as products of primes in this way. Okay, so this seems reasonable in terms of what we expect. That's what the statement is saying. Okay, so let me talk about some scratch work that we're going to end up doing in the inductive step later. That kind of will indicate why we're going to do strong induction and not just a regular weak induction. So in the inductive step, I will ultimately try to show that this statement is true for k plus 1. So if I let n be k plus 1, I'm going to be trying to show that k plus 1 is a product of primes. So maybe I'll be able to show, that, k plus 1 is some number a times some number b. Like if it wasn't already prime itself, maybe I'd try to show this. Maybe I'd try to show k plus 1 equals a times b. And if I could do the type of thing that I talked about earlier in the video, which is, if those two pieces that are multiplying together, if I knew that each of them was a product of primes, well, then I could just multiply those together. So scrolling back to where we are here, it's not going to be enough if I'm trying to show that k plus 1 is a product of primes just to assume that k, one step below k plus 1, is a product of primes. Because, you know, a and b might not be k. So I really want to be able to assume that a is a product of primes and b is a product of primes. And strong induction lets me do that. Because with strong induction, we get to assume that starting with whatever this begins, so this set begins at 2, we'll get to assume that 2 and 3 and 4 and everything up until the one before k plus 1, which is k, we'll get to assume that all of those are products of prime. So that list hopefully will encompass the a and the b. So we'll be able to say a and b are products of primes. Okay, so all right, so let's get into the proof. Ordinarily, I would flesh out the scratch work a little bit more, so I had a complete idea, but you know, due to conciseness, these induction videos always tend to be a little bit longer because the problems just tend to take a bit longer to think through. I'm going to dive into the proof at this point. So I'm going to put a little thought bubble around the scratch work. Okay, my proof. So let us proceed by strong induction. By strong induction on n. So I begin my induction proof by stating what P of n is. What is the statement we are trying to show? I'm trying to show that n can be written as a product of primes. P of n is n can be written as a product, I'm going to abbreviate product, is a product of primes. Okay, I'm trying to show that that's true for all integers n greater than or equal to 2. So now I do my base step. So because I'm trying to show it's true for all integers greater than or equal to 2, my base step isn't going to start at 1, it's going to start at 2. So my base step starts at n equals 2. So is this statement true for n being equal to 2? Well, yeah, we already showed that up here. 2 is just prime already, so it's a product of 1 prime. So I will say that n equals 2 is a product of 1 prime. So the base case is true. So the base step is true. Awesome. As we've seen in our previous examples, often that's the case, that the base step ends up being pretty quick to show. The inductive step is where the work really happens. So we start off the inductive step by saying, okay, I'm going to let k be an arbitrary element of whatever set we are trying to show the statement is true for, which is integers greater than or equal to 2 here. So I'm going to let k be an element of the integers greater than or equal to 2. And now I need to assume that P of n is true for all of these values, for 2 and 3 and 4 and everything up until k. Okay, so the way I can write that more formally is I'm going to assume that for all j that are integers that are between 2 and k, that P of j is true. Okay, so that is saying that P of 2 is true and P of 3 is true, and then everything up until P of k, we're assuming that all of those are true. This is what this is saying. It's just writing that a bit more formally without me having to write ellipses like this. Okay, so what does it mean if P of j is true? Well, that means that j is a product of primes. J is a product of primes. So no matter which j we pick, either between 2 up to k, which integer we pick between them, that integer can be written as a product of primes. So that is what we are assuming for the sake of strong induction. Okay, so just on the side, I'm going to write that down a bit more. So we are assuming that 2 is a product of primes. This is our strong assumption. We are assuming the following. So we're assuming 2 is a product of primes, that 3, I'm just going to put these quotes, which means I'm saying the same words. 3 is a product of primes up until k. K is a product of primes. We are assuming this. So let me put this in a little thought bubble. Okay. So what I need to do now is I need to make the jump to k plus 1. So let's go ahead and consider k plus 1. Okay, so there are two cases that I want to consider. So in the first case, well, what if k plus 1 is prime? What if we got lucky and this was already a prime number? Well, then it's a product of 1 prime. I don't have to multiply it by anything. It's already prime. It's a product of, whoops, sorry, I forgot to write the number 1. It's a product of 1 prime. So we are done in this case. Okay, so I love it when something like that happens. It's a bit less work. So if it's prime already, well, it's a product of 1 prime. So we would be done. Case 2 is the more interesting case, which is, well, what if k plus 1 is not prime? What if it's not prime? So recalling our definition from above, if it's not prime, if k plus 1 is not prime, well, there's two possibilities. Either it could be 1, or there's another positive integer that divides my number besides 1 and besides that number itself. So for us, well, remember, we said k is greater than or equal to 2, which means k plus 1 is greater than or equal to 3. So that means k plus 1 could not be equal to 1. So I'm just going to write a note of that in the margin. K plus 1 is greater than or equal to 3. So, k plus 1 cannot be equal to 1. That rules out that possibility, which means it's got to be the other possibility. There's got to be some positive integer a such that a is going to divide k plus 1. And moreover, a has to be something between 1 and k plus 1. In fact, let me restate the beginning part of that. If it's bigger than 1, that actually means it's greater than or equal to 2. So a is greater than or equal to 2, and it's got to be less than k plus 1. Okay. So, well, if a divides k plus 1, that means there's a positive integer b such that k plus 1 is going to be equal to a times b. That's what it means for a to divide k plus 1. There's something I multiply a by to get k plus 1. Okay, so what I have here now is, if I think back to my scratch work, I've established in this case that k plus 1 equals a times b. And what I'm really hoping is that the a and the b are both, one of these integers, something between 2 up until k. Because if they are, well, my assumption, my strong induction hypothesis was that all of those are products of primes. And so if I can show that the a and the b are both among this list, we are good to go. Okay, so, well, is that the case? Well, we've already said that a is greater than or equal to 2, and it's less than k plus 1. So a, well, we already got that a as part of that list. We haven't yet shown that about b. So let me write that down. I need to show that b is greater than or equal to 2 and less than k plus 1. Because if it is, that means b is also one of the integers in this list. Okay, so how do I do that? I am going to consider some cases and rule out the other possibility. So what if b was 1? If b was 1, and I look at this equation, k plus 1 equals a times b. Let's go ahead and plug in. This will just be equal to a times 1, which is a. So I'd get k plus 1 equals a, but I know a is less than k plus 1. So I started off with k plus 1, and now I got that k plus 1 is less than k plus 1? That doesn't make sense. So that's a contradiction. So there's a very common symbol for contradiction in math proofs, and that's to draw two arrows pointing at each other. So I'm just going to make a note of that. So this is a symbol for a contradiction. Symbol for contradiction, two arrows pointing at each other. So, if b was 1, it leads to a contradiction. So that means b cannot be 1. And we know that b is a positive integer. So if it can't be 1, well, that means b's got to be greater than or equal to 2. Okay, so that shows this part. b is greater than or equal to 2. Now I need to show that, well, b's got to be less than k plus 1. So let's see what happens if I suppose b is greater than or equal to k plus 1. Conceptually, I know that when I multiply the a and the b together, well, if b was k plus 1, that's already matching the k plus 1. And I already know that a is greater than or equal to 2, so I'd be multiplying something that's at least 2 with something that's at least k plus 1. And when I multiply those, that seems like it should definitely be bigger than k plus 1. And that's going to be my idea. So the way I show that more formally is, well, I'm going to replace the a and the b with things that I know are smaller than them. So I know I know 2 is smaller than a, so I'm going to replace the a with a 2. And I know that by this assumption that k plus 1 is less than or equal to b. So I've replaced both the a and the b with things that are less than or equal to them. So that means I will get an inequality like this. Because 2 is less than or equal to a, k plus 1 is less than or equal to b, so when I multiply these two things together, it should be less than or equal to a times b. Okay, so I got that a times b is greater than or equal to 2 times k plus 1, but that is bigger than just k plus 1, because this is a positive integer, and when I multiply that positive integer by 2, it's going to be bigger. So what I've shown here is that k plus 1, I started with that, is greater than k plus 1. That is, again, a contradiction. So contradiction. I'll write those arrows pointing in at each other. Okay, so I assumed in this case that b was greater than k plus 1. Because I got a contradiction here, I can say, so, well, that means, well, b has got to be less than k plus 1. And that establishes this other inequality. So with these two things put together, we have what we need about b. So it follows that b is greater than or equal to 2 and less than k plus 1. From earlier, I know the same thing about a. I'm just going to fill in these blanks with that same info. A is greater than or equal to 2 and less than k plus 1. Okay, so that means both the a and the b are part of this list that I have this assumption of. We said that for any of these positive integers between 2 and k, that they can be written as products of primes. We are ready to use that now. So by the inductive hypothesis, a and b can be written as products of primes. So let's go ahead and do that. So maybe the a, I don't know what the primes are that make it up, but I'll just call them some variables. Let's say a is a1 times a2. Let me put some multiplication symbols here. Times dot 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 times up until, and let's say it just goes up until an. So let's say a is a product of these primes. And let's say that b similarly is like b1 times b2 times dot 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 up until bm, where these ai's and bi's are primes. Well, now what I'm going to do is k plus 1, we said it was a times b. K plus 1 is a times b. Let's go ahead and multiply these equations for a and b together. Because a is a1 times dot 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 times up until an. I'll put that in parentheses. Times b is b1 times dot 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 times up until bm. The reason why I'm using different variables here for these subscripts is because, n is the number of primes multiplied together here for a. And m is the number of primes multiplied together for b, but those might be different. If I use the exact same variable for these subscripts, I'd be assuming that a and b have the same number of primes multiplying together to form them, which is not necessarily true. Okay, so what I have now is k plus 1 ends up being this set of primes multiplied by this set of primes. So overall, that is also a product of primes. Okay, and that is exactly what I wanted to get at the end, that k plus 1 is a product of primes. That completes the inductive step, and I'm ready to just state the final conclusion, which is by strong induction, the result that we were hoping to show holds. The result holds. Okay, and that completes the proof. Awesome, awesome. Okay, so a couple notes about this. The first is that weak induction would not have worked since the A and the B that we ended up breaking our K plus 1 down to, that K plus 1 was A times B, well, they were not necessarily equal to K. To be able to just use weak induction, I would need these things to be K, but that wasn't necessarily the case here. So strong induction lets us jump back more than one step. So the fact that A and the B could have been integers further back than just A, that was okay because of strong induction, but it wouldn't have been if we just had weak induction. All right. And there we have it, our first proof with strong induction.